Hello everyone. Let's start today's meeting. So yesterday I have to speak a bit out loud because there's no microphone in this room. If it's too much, let me know. I can make it lower as well. So yesterday we talked about memory robustness and RowHammer and RowPress problems in general. So today we will cover some of the cutting-edge research projects today. So they will be mostly Safari papers, but we will also cover some non-Safari works as well. I will give the first presentation. I hope to finish it in about like 25 minutes. But please don't hesitate to stop me and ask questions in between, okay? So the first piece of work is called Spatial Variation-Aware Disturbance Defenses. Okay, I forgot about this. So I forgot about this yesterday as well. So this is a brief self-introduction for myself. So my name is Giray. The full name is Abdullah Giray. It's important. So I've been doing research in Safari since August 2016 in different places, and I defended my thesis earlier this year. So I have a website over there for the full references, links to all the works that I did, and so on. And please don't hesitate to use my Gmail address if you have questions to reach me. So it's already in the slides. And I work on all fields of computer architecture and hardware security, especially focused on memory and storage systems. So let's move on to the paper. So the full title is, as you see over there, this is a paper that was published earlier this year in HPCA, High Performance Computer Architecture Conference, one of the top conferences in the architecture field. So we will talk about memory isolation as a quick background. Let's assume that you have this memory and this box represents your memory, and you have an access going to a certain memory location. And you observe data change from 1 to 0 or 0 to 1, it doesn't matter, in a location that is not actually in the location that you access, read or write. So it shouldn't happen, right? Because you didn't change that data. And when it happens, it can lose data loss or corruption. It can compromise your application's correctness. I gave some examples yesterday about those. It can be used to leak private information, like stealing your SSH keys. And it can be used to take over your computer to get the pseudo privileges, as I showed earlier. So to avoid this, we have the principle called memory isolation. Basically, it dictates that an access to one memory address should not have unintended side effects on the other memory addresses. And this is a really fundamental primitive in terms of security and privacy and reliability, basically for your data integrity in your system. However, it's difficult to satisfy in modern memory chips because we have DRAM technology as the main memory technology today. It's the prevalent technology because of a lot of trade-offs in terms of its density, access latency, and so on. And within a DRAM chip, this is the general organization. I'll just quickly go over it. So within a DRAM chip, we have multiple banks. And in each bank, we have these smaller arrays called subarrays. And within each subarray, we have DRAM cells organized in two-dimensional arrays of rows and columns. And as we discussed yesterday and last week as well, internally we access DRAM rows in a DRAM row granularity by fetching their data down to the row buffer. Okay, so inside the DRAM cell, as we discussed earlier, there's a capacitor that stores your data in terms of electrical charge, and there's an access transistor that you access this data. So there are several charge leakage paths, and it's a volatile memory technology, so it requires refresh operations that need to be performed so that you do not lose your data. And to access data, you need to first perform an operation called row activation to fetch the row's content into the row buffer. And then you perform the column accesses to the row buffer, as we discussed yesterday again. And once you're done with the row, you need to perform an operation called precharge to close this row so that you can open another row. So I'm just going to animate this. So if you open close DRAM rows very frequently, you have bit flips in neighboring cells, right? So this is called a RowHammer, and it's a prime example of DRAM read disturbance, as we discussed yesterday. Let's move to the executive summary of this paper. So, as you know, disturbance worsens with technological scaling. With newer chips, we have increased vulnerability, and existing solutions already have significant performance, energy, and cost overheads. And unfortunately, there's no rigorous prior work on the spatial variation of DRAM read disturbance across DRAM rows, and variations implicate and also the variations implications on future solutions. So in this work, our goal is to understand the spatial variation and read disturbance across these different DRAM rows and make that information useful to leverage that to improve the existing solutions. So in this work, we test 144 DDR4 DRAM chips from 3 major manufacturers, and we characterize all the rows in a bank, and we also characterize multiple banks inside the DRAM chip. And we find out that there is a large variation in the RowHammer read disturbance vulnerability of DRAM rows. When you look at different rows across all these, like across within a bank and across banks, and this variation does not follow a very regular pattern. So based on this finding, we come up with a mechanism with the key idea of dynamically tuning a given solution's aggressiveness based on the victim row's vulnerability level. And to this end, we propose a new mechanism called Svärd. Svärd stands for Spatial Variation Aware Read Disturbance Defenses. And it turns out that it's also the Swedish word for sword. So at some point, there can be a Godric Gryffindor sword appearing somewhere. I don't remember exactly where. So Svärd tunes the solutions threshold, performing preventive actions, performing some preventive actions, and it's implemented either inside the DRAM chip or in the memory controller. Okay, so we evaluate the effect of Svärd on existing defenses, and we show that it reduces the given solution's performance overhead quite significantly, and as a result, it provides some speed up to your system to concurrently run in benign applications as well. Okay, so our motivation is about technological scaling. As we go to smaller chips and chips get closer to each other, we have more than an order of magnitude reduction in the minimum activation count we need to perform to induce a bit flip. I think when Nisa is presenting, she will also show like 2 orders of magnitude reduction. This slide is a little bit stale. And DRAM read disturbance worsens as DRAM chip density increases, and existing solutions become quite aggressive. And this aggressive prevention makes them prohibitively expensive going forward. And the problem is that no prior work actually rigorously studies the spatial variation across different DRAM rows and the variations implications on future solutions altogether. Our goal is in this work is to understand this variation and also to leverage this understanding to improve existing solutions. Okay, let's move to the experimental characterization. So I talked about this infrastructure a little bit yesterday. Later on today, we will also talk about it in more detail. But this is the infrastructure that we call DRAM Bender. So DRAM Bender is an FPGA design actually that we download to an Alveo board. It's some board that you can just buy from Xilinx. And it also supports like several other FPGA boards as well. And we connect the DRAM module and press it with heater pads from both sides. And the heater pads are controlled with a temperature controller, and we have a PCI host interface that connects this FPGA board to the host machine so that we can run our tests and we can analyze the experimental data. So the important thing is we have fine-grained control over DRAM commands with the granularity of 1.5 nanoseconds, and also we can control temperature with a precision of 0.5 degrees Celsius. In this work, we test these modules. So there are a lot of details here, and there are a lot of details in the paper as well. I'm not going to go over them, but these modules are essentially from 3 major manufacturers. So when you sum up the market share of these 3 major manufacturers, you reach to like 98.5% of the market share or something like that. So if you just go to Amazon or Galaxus and buy a DRAM chip randomly, probably you will hit one of these. And we cover different densities, die revisions to see like if our observations are correct across generations as well. And they implement different chip organizations as well. So these are like different kinds of chips from these manufacturers. And our key takeaway at the end of the characterization study is that read disturbance vulnerability varies significantly and irregularly across DRAM rows. And I will show you a part of the characterization data here. So in this plot, on the x-axis, we look at this is a histogram, by the way, this is a distribution plot. So on the x-axis, we look at the minimum hammer count to induce the first bit flip, or HC first. And on the y-axis, we look at the fraction of DRAM rows that exhibit this behavior. And different colors of bars represent different DRAM modules. And this is all from the manufacturer S, which is Samsung. So here are some observations. Okay, we also show the variation across banks with the error bars. And yeah, the first observation, the worst HC first that we observed across these 5 modules is 12,000 activations per aggressor row in a double-sided access pattern. And when we look at the this parameter across different DRAM rows, we observe that there is a very large variation. So if you look at like S4 here, for example, you can find DRAM rows that experience bit flips at 12K activations, and there are also rows that do not experience any bit flips until 128K activations. So it doesn't make sense to protect these two sets of rows with the same robust rigor, essentially. Okay, so the minimum hammer count to induce the first bit flip significantly varies across rows in a DRAM bank. And we just collect the same data for like other manufacturers as well. So I'm showing you these, and then I'm gonna conclude with the same message. And there are more details, and we have like all these minimum, average, and maximum RowHammer thresholds across DRAM rows for each module in the paper. You can go ahead and check all this data if you're curious. It's available on this archive link. Okay, so let's look at the regularity in the spatial variation across DRAM rows. So on the x-axis now, we have the DRAM row address going from 0 to 64K. 64K corresponds to like 64 times 2 to the 10. So it's like 65,536, something like that. On the y-axis, we look at the minimum hammer count to induce the first read disturbance bit flip, and this is how it looks. So you might think that there are some patterns here. It's only because like we only test a small number of different HC first values on the y-axis. So pretty much like it's hard to say that, oh, there is this like repeating pattern here, or there is a correlation between the row address and the HC first value. So our conclusion is that there's no visible regularity to my eyes based on the row's location. And the minimum hammer count to induce the first bit flip irregularly varies across different DRAM rows. That was one module from SK Hynix. This is another module from Micron. This is another module from Samsung. And none of them show very clear patterns. Let's look, and sorry, go ahead.
So along one row address, you have multiple points. Is that because of the different types that we have?
Oh, it's just about the resolution of the image, basically. So you have like, so those dots should be like in different rows, actually. Okay. It's because like this x-axis is like zoomed out quite a bit, right? Yeah. So far what I showed you is just like eyeball statistics, right? I just look at the picture with my eyes, and I say I don't see anything. Okay, it's not very scientific. So we tried some statistical approach. So we looked at the predictability of a DRAM row's read disturbance vulnerability based on several spatial features that a row has. So we looked at the bank address bits. We looked at the subarray address bits, row address bits, rows distance to local row buffer. So these are the spatial features that we can come up with, right? And then we looked at if we can look at these properties or features, and then based on these features, can we predict the read disturbance vulnerability level of a DRAM row? And we clustered DRAM rows into like 15 different bins of RowHammer vulnerability. and we try to cluster them based on these features, basically. And we measure the F1 score for each spatial feature, and the result is that only a few of these spatial features, by a few, I mean like among all these bits, you only have like a few bits, and it's only for the DRAM modules from Samsung that show some F1 score that is above 0.7, which is really not a great F1 score anyway. So we couldn't find a good prediction based on these features. So this is an open resource problem, right? So it doesn't mean that there is no feature that we can use to predict, or it doesn't mean that there is no correlation as well. You might look at the data, you can analyze it maybe in a better way, and then you can find a better correlation or better relation in between. So the disturbance vulnerability, so far as we can investigate, very significantly and irregularly varies across DRAM rows. And this is the full paper. So based on this, we designed a new mechanism called Svärd. So our key experimental takeaway is just repeating there. It varies significantly and irregularly. So our idea is to leverage the variation across DRAM rows to enhance our mechanism, the existing mechanisms. So our mechanism is spatial variation where read disturbance defenses, and it dynamically tunes the aggressiveness of an existing solution to the victim row's read disturbance vulnerability. And Svärd essentially performs fewer preventive actions if your row is more resilient to read disturbance bit flips. And by doing so, it reduces the number of preventive actions, preventive refresh operations that you perform in your system. And as a result, your performance overhead reduces, and your system performance improves. So we can integrate we can integrate Svärd with like any given solution today. I think it might sound like a bold claim, but I can substantiate it if necessary. But in this paper, we cannot test with like all the mechanisms in the world, right? So we chose like 5 solutions that are relatively new and state of the art, and we integrate Svärd with those solutions. The first one is Para. So if you remember from yesterday, what Para does is that when a row activation comes, it generates a random number, and based on that random number, it refreshes the neighboring victim rows or not. So to make that decision, you basically generate a random number and compare the random number against the threshold value. And what Svärd does is tune in this threshold value. For RowHammer, it's another paper that we might talk about in the future. We count the number of activations per DRAM row using some filters, and the activation counts are compared against the threshold. So we change the threshold so that we can change the aggressiveness of RowHammer. The same story for another mechanism called Hydra. Again, there is a threshold. So if there's a threshold in your mechanism's decision-making process, then we can change the threshold by using Svärd, and we can tune the aggressiveness of your mechanism. Okay. So Svärd classifies DRAM rows into several vulnerability level bins and maintains just a few bits per DRAM row. Let's say we define like 16 different clusters, and then we classify the DRAM rows into these 16 classes, and we can identify which class a row belongs to by using 4 bits, right? So we just maintain those bits, and we can maintain those bits inside the DRAM chip or inside the memory controller, and the decision is based on wherever your existing read disturbance solution is. The memory controller based implementation, if your solution is implemented inside the memory controller, then you can so then it looks like this, right? So you have the memory request scheduler, you have DRAM chip, you send DRAM commands and address data, and this purple box is your memory controller. And you might implement your existing read disturbance solution, let's say Para, in the memory controller. And in that case, you need to access this information within the memory controller to make a decision. So you can add an additional HC1st table here, and you can feed the row address to this table, and then this table just gives you which HC1st value to use. On Zoom?
Yes.
I want to encourage people on Zoom to just speak up, but for now, I guess you can just convey the question.
Is a row vulnerability relatively constant, or would it change with different data pattern or with time?
So it changes with data patterns. So that's part of the profiling process. Should I repeat the question actually? Maybe I should repeat the question. So the question is, does a DRAM row's read disturbance vulnerability change over time or with data patterns or somehow?
Yeah.
So it depends on temperature, as we talked about yesterday. It depends on the data pattern. It depends on some other stuff as well. So there are some sensitivities. So in your profiling, you need to account for them. About time, I will talk about it later. So I'm not going to give the answer yet. So here you can feed the row address to AC1st table and understand which cluster this row belongs to. Or you can choose to put your metadata inside the DRAM chip so that, as you know, like DRAM has a higher density compared to SRAM, for example, right? So if you implement or maintain this metadata in memory controller, then you need to implement it with SRAM kind of structures that can be a bit costly for you. Probably not. Actually, we evaluated. It doesn't seem very costly, but if you consider that as a costly implementation because it's a subjective decision, you can also implement them inside the DRAM chip. And when you read data from DRAM chip, you can also read these metadata bits along with the data because you have some additional bits that you read in most cases, like ECC bits, for example. There are some pins that are not used in certain cases. So you can utilize them to access these metadata bits. So in that case, you move everything to the DRAM chip, right? So not everything, the metadata inside the DRAM chip. So you can basically implement this in two different potential ways. And if you implement this inside the DRAM chip, then this is how it looks. So inside the DRAM chip, you have a I/O periphery, you have a refresh controller, and then you have your existing read disturbance solution here that actually enqueues some refresh requests, and you have your DRAM subarray here. So what you do, this is one way of implementing it. You can implement it in many other ways. In architecture, we have usually like several different solutions. You can explore the design space and find Pareto optimal points. But this is just one example. So in a DRAM row, you have 8 kilobytes of data. So you need additional 4 bits for 8 kilobytes of data. Or if you're considering like, okay, we have multiple chips and we lay out our row, so you have 8 kilobits of data in a DRAM row, and you add 4 additional bits next to it. So it's a very low overhead. Yes.
So PC first needs to be stored by profiling before usage.
Yes.
But then that also exposes it to reliability concerns.
What concerns?
Reliability concerns. Say, because it's in the same row. Can that also be exposed to RowHammer or let's say RowPress?
Yes. So you protect this. Okay, I will repeat. So we put the metadata inside the DRAM row, and DRAM row is already vulnerable to read disturbance. So can those bits change? So ideally, you don't want you don't want any bit to change in DRAM row, right? So the basic assumption is that your existing read disturbance solution over there is already counting activations and refreshing your row when necessary, so that there's no bit flip in your row. So when you do the profiling, you do the profiling for those bits as well, actually, right? So if you protect your row, those bits are also protected. Okay, let's look at performance evaluation. We use Remulator 2.0 as our simulation framework. I'm going to talk about it later today. And we evaluate a realistic system. We test the system with 120 different 8-core multi-program workloads. And we pair Svärd with 5 different mitigation mechanisms. And we sweep the HC first value, which is the minimum hammer count to induce first bit flip, from 4,000 down to 64. Okay, so on the x-axis, we look at the minimum hammer count to induce the first bit flip. And on the y-axis, we look at the system throughput by using the metric called weighted speed up. And this is how para looks when you do not implement anything. So purple is no Svärd, right? So we don't have Svärd here. As we reduce the RowHammer threshold, this is the minimum number in the bank that you can find. Para reduces system performance quite significantly. And then once we apply three different variation profiles that we collected from these real modules, H1, M0, and S0, these are like a module from each manufacturer. When we integrate Svärd with Para and use these profiles, we have this kind of results. So I guess it's clear that we reduce the performance overhead of Para quite significantly here. And these are the results for the other four mechanisms. And these are the speed up numbers that you see in like very low extreme thresholds. And Svärd significantly reduces the performance overhead of existing solutions, basically. Okay. So we have many other things in the paper that I will not cover. So we look at the bit error rate distribution. We look at how it works with RowPress. And we have a lot of details. We have some reverse engineering data. We look at hardware complexity of the mechanism, and we show that it can be implemented at low cost. And we also have a preliminary analysis of the effect of aging. Actually, I have a slide about that I will show you. Okay, this is that slide. So I will go back to the previous question that we had from Zoom. Does the vulnerability profile change over time? So this is a really important question for this kind of mechanism. And I'm going to show a weakness of this mechanism actually at this point. So what we did was like we just kept hammering some rows for many days. And then I already showed this data to you yesterday actually. And we observed that for some of the rows, your threshold can reduce over time as you hammer it. So this means that if you use something like Svärd, you have several options again. You need to repeat profiling quite often, maybe not that often. So we don't know that because we don't know how aging works with read disturbance, really. This is just some preliminary data. This is just to motivate further aging studies. So we need to understand how aging works. And based on that, we need to periodically repeat profiling our chips. Maybe we can find some online profiling tools that, you know, while you're using chip, you can block a part of it, and then you can do the profiling over there, for example, and update your profile. So Svärd is nice in the sense that once the behavior of your row changes, you can just update the metadata, and then it works fine. But you need to have some mechanisms to update that metadata. So there is some further research opportunities over there. And I want to encourage you to work on that. Okay. So in conclusion, we did the first rigorous experimental study on spatial variation among a lot of chips, and we show that read disturbance vulnerability significantly and irregularly varies across DRAM rows. Our key idea based on this observation is to dynamically tune a given solution's aggressiveness. And to this end, we propose a mechanism called Svärd. It tunes the solution's threshold of performing preventive action, and it's implemented either inside the DRAM chip or in the memory controller, and it significantly reduces the performance overhead of existing solutions. And this is the end of my slides. I can get further questions. Yes, which one? Okay.
So you showed that you actually speed up, but you also like you manipulate the thresholds, so does that affect the performance, like the bit error, like doesn't change, or does it stay the same because it could change?
So, are you talking about this?
Yes. So you showed that you get speed up.
Speed up based on the like our baseline is para without Svärd in this case, right?
And then it shows that you still have the same like accuracy.
You mean seems reliability though?
Yeah.
Yeah. So we have a security analysis of that as well, actually. So basically, so if you're talking about this point, for example, the RowHammer threshold is 64, right? So in 64, it means that the worst row you have in your bank experience bit flips at 64, and you have other rows that will not observe bit flips, experience bit flips until like 10,000, for example. So in Para's case, it just keeps using the same threshold for all rows. But in our case, we just use the proper threshold for each row based on this like variation profiles that we collected from real chips. So in that case, the security level of rows are the same. So Para basically was making some rows like extra secure. So we that's the trade-off. We don't make them like unnecessarily extra secure.
Yeah, I was wondering, so you compare the quality for your implementing, either in my controller or in the DRAM chip.
Yes.
I was wondering if this is that like you do comparison the paper between these two. And if so, have you implemented this in the hardware or like only for simulator level again?
No, it's just simulation work. Well, there is like experimental characterization of real DRAM chips, so that part is real. But the mechanism and the implementation of the mechanism are just like we basically estimated the cost based on some models that we keep using in the community. Yeah. Yes.
Does paper include what percentage of rows have, say, for example, the requirement of 46 as the minimum? Is it a small percentage or a big percentage?
Yeah, so the weakest rows are actually very small fraction. And yesterday I showed some other characterization data. It's coming from another paper that tells you that if you look at like 10% of the rows that are the weakest rows, and you compare it with the 90% of the rows that are the remaining rows, this you need like double the activation count to achieve a bit flip compared to the 10%. So there's a very small fraction of DRAM rows that are like significantly more vulnerable to RowHammer. And I think you can find those numbers in those like histogram plots, and the table has minimum, maximum, and average. It doesn't show the population. Yeah.
So, I mean, could it make sense to expose this information to the memory allocator to leverage even more speed up so that you access the weak rows much less?
So that's a very good point. The question is, does it make sense to expose this information to the to where? The system? To memory allocator, yeah. System software, exactly. So when you do this hardware software cooperation, basically, whenever you do that, you get something really significant out of it. So it's a good direction. And you can expose this information, so you can put your security critical data into very like very resilient rows that do not observe bit flips. Then it's very good, right? Then you don't have to keep refreshing all of rows. And if you can also implement something inside the memory controller, for example, that understands like which rows are allocated, which rows have some garbage data that I will never use. If you can pinpoint them, like there's definitely some benefits over there. I'm gonna refer you to a paper called Expressive Memory. It was published in, what was it, 2018, 2017? 2018, right? It should be ISCA 2018. Expressive Memory. Yeah. Maybe we can cover it in some other lecture as well. I'm not sure if it's in the plan, but we can definitely include it. Yes, go ahead.
There's only such a small percent of the rows that actually look like very vulnerable.
Yeah.
Only because like just measure that in the manufacturer and just turn on those rows in the same way that some computer manufacturers do.
So I'm just guessing that they're already doing that, because when they manufacture DRAM chips, they actually, let's say you have like, you want to have 64K different rows inside a bank, right? By design. They don't implement like that many rows, they implement more rows. And they have something called spare row. So after the manufacturing process, they test their DRAM rows. Some of them turn out to be faulty, and they don't want to just like trash that chip. So they have some remapping table inside the DRAM chip that redirects some row addresses to other row addresses. So that kind of thing is already done to improve the term is yield, like to improve the manufacturing throughput, basically. And I think it's not very unrealistic to guess that they're already doing this as well. But these are the chips that we just buy from Galaxus, for example, right? So it's not really like before those tests. They already went through those process. Yes.
Part of it stored, like only changes the threshold of, or is there any other method that is?
So in this mechanism, we just change the threshold.
And as well as for other solutions like Aqua and some
Yeah.
other solutions, those are only threshold values.
Yeah, so I didn't go through this in detail because it's the same story. So for all these mechanisms, you always like count something, calculate something, and compare it against the threshold. And once you change the threshold, you actually change like how frequently they decide to perform preventive refreshes or not. Or like in RowHammer's case, it throttles accesses. So it decides throttle or not throttle based on some threshold. So when you change the threshold, you can make a difference in that decision.
So the threshold is decided by the profiling of every DRAM.
Yes.
So this profiling changes, let's say, with the data distribution across all the. So how frequently the profiling needs to be done again to have, let's say, stored effective.
So everything based on the profiling data, and all these mechanisms, by the way, have their own security analysis in those papers. And the security analysis starts with the basic assumption of that I have the HC first value, or I have the RowHammer threshold. And that's a correct information. And if that information is not correct, the security analysis is just garbage for all these, right? And it all depends on the profiling data. It all depends on your testing methodology, how rigorous you go with the testing methodology. And as like we discussed yesterday, the vulnerability level changed a lot with temperature, a lot with data patterns, with access patterns. So you need to really find the absolute worst case to find the correct RowHammer threshold. And it's not practical to do today, let alone the effects, potential effects of aging, for example. So that profile can change over time. And even if we assume that it doesn't change, it's really hard to gather that profile as well. And it's an active research problem, actually. So I don't have a very good question to that because we don't have a solution for that. And we need to do like more tests. We need to understand how this works better. By this, I refer to like the error mechanism, the disturbance phenomenon. We need to understand how it works in a more detail so that we can develop better tests to find those worst cases. So there's a lot to do in that front.
When the profiling involves counting the minimum number of hammering per row or something else.
So you basically test hammering rows with some number of hammer counts. And then you observe if there's a bit flip. And based on that, you reduce the number of hammer counts or increase the hammer count. So you try to find the minimum hammer count you can induce a bit flip. And then based on that, you tune your or configure your mitigation mechanism. Are there other questions? I guess it's already time to move to the second talk, right? Maybe we're a little bit late even. But it's good. Keep asking questions.
So in this part of the lecture, we will talk about low-cost and scalable RowHammer mitigations. Is everything okay? Okay, so let me start with a introduction. So hi, I'm Nisa. I'm a researcher in SAPA Research Group since September 2018. I started my PhD almost 2 years ago, and you can contact me with this email. And my research interests are computer architecture, hardware security, with a more focus on memory systems. So let's continue with some RowHammer mitigations. I guess you are already familiar with the slide and the concept, but today's DRAM chips are vulnerable to read disturbance, where repeatedly opening and closing or activating and pre-charging the same DRAM row results in bit flips in nearby DRAM slots, which we call RowHammer bit flips. And we refer to the hammered row as the aggressor row, and all other rows with the bit flips are called victim rows. And we call the minimum number of activations that cause the bit flip the RowHammer threshold. And again, as you all know, DRAM chips are getting more and more vulnerable to read disturbance today. And read disturbance bit flips occur at much lower activation counts. So this is the first work that looked into read disturbance errors, and it reported this high RowHammer threshold. And these two more recent works from 2020 and 2023 reported much lower activation counts, resulting in read disturbance bit flips. So the RowHammer threshold has reduced more than 2 orders of magnitude in less than a decade. And this is exactly why mitigation techniques against read disturbance attacks need to be effective and efficient for highly vulnerable DRAM-based systems. One way to mitigate RowHammer is to preventively refresh potential victim rows when an aggressor reaches a dangerous activation count, but doing so requires tracking DRAM row activation counts of the aggressor rows before these victims experience bit flips. And let's look at an overview of approaches to track DRAM row activation counts. So the first approach that comes to mind is to allocate one activation counter per DRAM row. Here we have, like each of these DRAM rows have one counter specifically for them, and whenever a row is activated, we increment one counter. So this gives us the perfect tracking mechanism. The mitigations based on this approach have very low performance and energy costs because they can do preventive refreshes when it is absolutely necessary. But as you can imagine, the area costs are getting very high because we have many DRAM rows in today's DRAM devices. So we need to store a lot of data to just track these activation counts. And the second approach aims to reduce the number of counters using one observation. This observation is that an attacker can only hammer a small set of the DRAM rows before DRAM is periodically refreshed. So this reduces the number of counters that we need. However, we need to allocate these counters to specific rows. So these approaches, these mitigations, allocates one activation counter per aggressor row. And they use tags to understand which counter belongs to which DRAM row. And again, since these counters are incremented when these specific rows are activated, the performance and energy costs are still low. However, especially at low RowHammer thresholds, the area cost is getting higher. This is because the number of aggressor rows increases significantly. When an attacker can induce RowHammer bit flips with fewer activations, this means that they can hammer more DRAM rows, and we need to track more counters. And since we are using tags for these counters are usually implemented with content addressable memory, which is also expensive when you consider area. And the third approach reduces number of counters and allocates less than one counter per DRAM row, either by introducing shared counters that group some DRAM rows to track them together, or by introducing probabilistic refreshes. And since we are reducing the number of counters that we implement, the area costs are low. However, especially at low RowHammer thresholds, the performance and energy costs increase a lot. This is because of the high DRAM bandwidth consumption that these mitigations have. So these mitigations use the DRAM bandwidth to do the preventive refreshes, and they do unnecessary preventive refreshes because they are not tracking the activation counts perfectly. And basically, they are doing preventive refreshes when they can do regular memory operations. And ideally, we would like to achieve low energy, low processor chip and DRAM area, and low performance overheads. And we looked at 4 state-of-the-art mitigation techniques. And as you can see from this radar chart, none of the existing mitigation techniques prevent RowHammer at low area, performance, and energy costs at the same time. And today I'm going to talk about 2 papers tackling this issue. The first one is called CoMeT, Count-Min Sketch-Based Row Tracking to Mitigate RowHammer at Low Cost, which was presented in HPC 2024. So our goal, again, is to prevent RowHammer bit flips with low area, performance, and energy overheads in highly RowHammer vulnerable DRAM-based systems. we observe that there are two types of counters. First one is hash-based counters that are low cost, and the second one is tag-based counters that are highly accurate. So we want to get the best of both worlds. We want to achieve both low cost and also high accuracy. I will explain how we achieve that, but before, let me explain how these counters work. So we have many DRAM rows in our DRAM device, and we have some counters that we want to map these DRAM rows to. And hash-based counters do this mapping using hash functions. So they take the row ID and give it as an input to the hash function and get the output of the hash function and use it as an index to the counter table. So this effectively maps each of these DRAM rows to these counters, one of the counters in the counter array. Since we are using hash functions, hash-based counters can be implemented with low-cost structures because they can do the mapping without using tags. And also, they can aggregate many rows activation counts together because we are basically representing this information with a fixed number of counters. So these two things make hash-based counters low cost. However, as you can see here, hash-based counters have one downside, which is some counters are shared with some DRAM rows share one counter. And in this example, whenever we have an activation row 0 or row 4, we increment the same counter. So this introduces a little bit of inaccuracy. And tag-based counters have the benefit in that case because each of these tracks one row's activation count, and we basically tag these counters with row IDs, and we increment just one counter when a specific DRAM row is activated. So this gives us high accuracy. And our key idea is to use low-cost and scalable hash-based counters to track most DRAM rows activations with low area, and use highly accurate tag-based counters to track only a small set of DRAM rows to achieve low performance overhead. And to this end, we propose CoMeT. CoMeT has two key structures. The first one is the counter table, which maps each DRAM row to a group of hash-based, low-cost hash-based counters as uniquely as possible using an algorithm, frequent item counting technique called the count-min-sketch technique. And it triggers a preventive refresh to an aggressor row's victim rows when the aggressor's counter group reaches an activation threshold. This way, the counter table tracks DRAM row activations at low area cost. And the second structure is called recent aggressor table, and it allocates highly accurate per DRAM row counters for only a small set of DRAM rows that are activated many times. And this helps us reduce performance penalties by increasing tracking accuracy. And this is a high-level summary of how CoMeT operates. When there's an activation to row A, CoMeT first checks the counter table that implements hash-based counters and gets an estimation based on that. And at the same time, it checks the recent aggressor table that has tag-based counters and gets another estimation. And CoMeT uses the recent aggressor table-based estimation when there's a tag match, because we know that tag-based counters are more accurate. And after that, CoMeT compares this estimation of the activation count to the preventive refresh threshold. And if that activation count reaches the threshold, it preventively refreshes victim rows. And there are more details, operational details for CoMeT in our paper. I invite you to read that if you're interested in it. And let's look at the evaluation methodology. So we evaluate the performance and energy consumption using cycle level simulation using a remulator and DRAM power. These are the system level configurations that we use for the simulation. We compare CoMeT against 4 state-of-the-art RowHammer mitigation techniques, namely graphene, Hydra, Rega, and Para. And we evaluate all these mitigations across many single core and 8-core workload mixes. And all our data and all our source code is open source, and you can check it out from this link. So we analyze, let's continue with the hardware implementation and the area analysis. We analyze storage and area overhead using cacti, and this is the comparison of CoMeT against graphene and Hydra for the RowHammer thresholds of 1K and 125. This is the area overhead of CoMeT. So as you can see, when we decrease the RowHammer threshold, CoMeT has actually a lower area overhead. This is because when we go to lower RowHammer thresholds, we need to store fewer bits for the counters. And this reduces our area overhead. And this is graphene's area overhead. As you can see, it's much significantly larger than CoMeT's area overhead. And this is the area overhead of Hydra, which is pretty similar to CoMeT's area overhead. So we conclude that CoMeT incurs a significantly less area overhead than graphene and a similar area overhead to Hydra. Let's look at the performance and DRAM energy overheads of CoMeT. So we evaluate the average performance and DRAM energy overheads of CoMeT across single core applications here. And this is CoMeT's performance normalized to a system with no RowHammer mitigation across different RowHammer thresholds. And as the RowHammer threshold decreases, CoMeT has a small performance overhead over the baseline because it issues preventive refreshes as opposed to no mitigation being in the system. And this is CoMeT's DRAM energy consumption normalized to the same baseline, and it shows a similar result. So we conclude that CoMeT prevents bit flips with very small average performance and DRAM energy overheads compared to a baseline with no RowHammer mitigation. And this is the performance comparison across single core applications of CoMeT against 4 state-of-the-art mitigation techniques. And this is the results for the RowHammer threshold of 1000. And when we go to lower RowHammer thresholds, as you can see, all mitigations have some performance overhead, increasing performance overhead, because they all start sending preventive refreshes. And here, we see that CoMeT outperforms all low area cost mitigations starting from the RowHammer threshold of 500. And we conclude that CoMeT incurs a small performance overhead over graphene and outperforms Hydra at all RowHammer thresholds. And this is the same analysis across 8-core multi-programmed workload mixes, and the trends are pretty similar to single-core ones. And this is the same analysis, but for DRAM energy comparison. This is single-core applications. And as you can see, all mitigations have some energy overheads because they are starting to issue more and more preventive refreshes. And we see that CoMeT still consumes less DRAM energy than all low area cost mitigations for all RowHammer thresholds. And it incurs a small DRAM energy overhead over graphene and consumes less DRAM energy than Hydra. And yes, these are the multi-core workload results. And again, they are pretty similar to single-core ones. We have more results in the paper, starting with the security analysis of CoMeT, which shows that CoMeT prevents all RowHammer bit flips at all RowHammer thresholds. We have a sensitivity analysis, sweeping some configuration values with more details and explanations and insights. And we have CoMeT's performance under adversarial workloads when there is an attacker run at the same time in the system, a comparison against throttling-based mitigation techniques, and performance evaluation at high RowHammer thresholds. CoMeT is open source and artifact evaluated, and I invite you to check our GitHub repo. So let me conclude this part of the talk. Our goal is to prevent RowHammer bit flips with low area, performance, and energy overheads in highly RowHammer vulnerable DRAM-based systems. Our key idea was to use low-cost and scalable hash-based counters to accurately track DRAM rows. We propose CoMeT, which tracks most DRAM rows with scalable hash-based counters, employing the count-min-sketch technique to achieve a low area cost, and tracks only a small set of DRAM rows that are activated many times with highly accurate per DRAM row activation counters to reduce performance overheads. And our comprehensive evaluation shows that CoMeT achieves a good trade-off between area, power, and energy costs, outperforming state-of-the-art mitigation techniques. So I can take your questions about CoMeT, and then we can move on to the other paper. Yes, please.
There was one talk which showed that CoMeT had lower area requirement and the threshold was lower.
Yes, the area overhead. This one. So usually when we go to lower, oh yes. So the question is, why does CoMeT has lower area overhead when we go to lower RowHammer thresholds? So let me explain the other mechanisms first. So when we increase the number of aggressors, the other mechanisms basically need more counters because the aggressors are increasing significantly. But with CoMeT, since we can use just a fixed number of counters and represent that information by sharing some counters and introducing tag-based counters as a backup mechanism, we can keep the same table. And when we go to lower RowHammer thresholds, we can represent that counter value with less bits. So the table size, the elements, number of elements are the same, but the counters are getting smaller. That's why we have a smaller area.
Yes, you don't necessarily comment about like with the hash-based counters. You do need a reversible hash function.
So we don't need a reversible hash function because, so let me maybe go back to the mechanism slide so that I can maybe point to things. So let's say that we have an activation to row A and we check the hash-based counters. We basically get like an estimation out of a group of counters that are accessed with hashes. And let's say that the other part is not important. There is no tag match. So what we do there is we assume only the row A is activated that many times and refresh its victims. And we don't do anything for the other DRAM rows that might be sharing the counter. But the next time they are accessed, the counter value is still over the threshold or at the threshold, so they are also being refreshed. Any more questions?
Should we take a break now or after Abacus?
Both are fine, I think. Okay. So I expected to take less time because we already covered the background and the goal. So the second paper is called Abacus, All Bank Activation Counters for Scalable and Low Overhead RowHammer Mitigation, which was presented in Using Security 2024. And the problem is the same. No existing mitigation technique prevents RowHammer bit flips at low area, performance, and energy costs. And our goal is to fix that, especially at very low RowHammer thresholds. Abacus' key idea, which I will talk about in the next slide, is based on this key observation that we make on how workloads interact with the main memory. I will show what we observe over an example. And here is a system with a CPU and 4 DRAM banks. And as you can see, each DRAM bank has a DRAM row at the same row address, highlighted with label row X. And a workload running on the CPU generates this load request targeting bank 0 and row X in the beginning of this timeline. Okay. So the CPU issues the request to its target bank and row, and it repeats this access pattern for other banks. There might be other requests targeting different rows at the same time, but this does not contradict with our observation. Eventually, the CPU accesses the same row address across all banks. And we call the rows with the same address sibling rows. There are two causes for our key observation. First one is the intrinsic spatial locality in workloads memory access patterns. So a program usually accesses neighboring access blocks at around the same time. And the prominent access pattern that leads to this behavior is streaming through the elements of an array. And the second cause is modern physical address to DRAM mappings that place neighboring cache blocks into different banks, but into the same DRAM row. And they do this to leverage bank level parallelism to get the most out of the available DRAM data transfer bandwidth. And this plot shows our key observation across many tested workloads. I will not go into too much detail of this, but I will explain what we did. When a row gets activated, RowHammer threshold times, which is 500 in this figure, we record the activation counts of that DRAM row's siblings. So each box in this plot shows the distribution of sibling rows activation counts for a tested workload. So above this horizontal green line in the figure shows that if a row is activated RowHammer threshold times, its siblings are activated more than half the RowHammer threshold times. And therefore, if we can track the sibling with the, if we can track the sibling that is activated the most, we can get a good estimate for the activation counts of all its siblings. And we repeat this analysis for a smaller RowHammer threshold, 125 activations. And we find the key observation to be more prominent at the smaller RowHammer threshold. Let me quickly introduce an important problem that we did not talk about existing per bank activation counter-based mitigation techniques. There are many banks in a DRAM chip. So the number of banks and thereby the number of activation counters increase with the newer DRAM generations. And we have already seen that sibling rows have similar activation counts, and our key idea based on that is quite simple. It is to use one activation counter for all sibling rows and reduce the number of counters by a factor of the number of banks. And Abacus' objective is to track the maximum activation count across all sibling rows using just one counter. If, for example, the activation count of sibling rows look like this, then the Abacus counter value for the sibling rows will be equal to or be larger than 97. Why? Because if the Abacus counter is smaller than the maximum activation count, we cannot mitigate bit flips. Therefore, this would make the mechanism not secure. If it's larger, we will have increased performance and energy overheads from unnecessary preventive refreshes, so we will have lower performance. And because of these two reasons, our key design goal for Abacus is to keep its counter value equal to the maximum activation count. And our implementation of Abacus leverages one prior works, namely graphene's activation count tracking mechanism. And for more details on how we implemented this, Abacus, please check the paper. So let's move on to the evaluation. So this is pretty much the same as the one I showed you earlier. And let's move on to the single core performance and energy overheads of Abacus. We show here the system throughput on the y-axis across all single core workloads for the RowHammer thresholds that are in the x-axis. And the higher the bar here is, the better. And this is the DRAM energy overheads. A smaller value is better here. And we conclude that Abacus prevents bit flips with very small performance and DRAM energy overheads compared to the baseline with no RowHammer mitigation. And this is the 8-core performance comparison of Abacus against these state-of-the-art mitigation techniques. And this is the full plot. And here are the boxes for Abacus showing the distribution of performance across all tested workloads. And the red boxes show the mitigation and RowHammer threshold configuration, which Abacus outperforms. And we observe that Abacus outperforms Hydra and Para at all RowHammer thresholds on average across all workloads. And we also see that Abacus incurs a small performance overhead over graphene, which we attribute to Abacus's unnecessary preventive operations due to its low-cost aggressive row activation tracking mechanism. Here's the same plot, but for DRAM energy, and we observe that Abacus consumes less energy than Hydra, Rega, and Para at all tested RowHammer thresholds. And for example, starting from the RowHammer threshold of 1K, actually, and for example, Abacus consumes approximately 20%, 70%, and 34% less energy than Hydra, Rega, and Para at a very low RowHammer threshold of 125. And Abacus performs similarly to graphene in terms of DRAM energy. That is only 4% higher at the lowest RowHammer threshold that we tested. Let's look at the area overhead of Abacus. And we again did this analysis using cacti. And this is a comparison against graphene and Hydra. And as you can see, at the RowHammer threshold of 1000, Abacus induces a significantly smaller area overhead than graphene, and it takes up smaller area than Hydra. And at the lowest RowHammer threshold that we tested, which is 125, Abacus takes up significantly smaller area than graphene, but Hydra's area overhead is actually smaller than Abacus. But you know that it comes with a great performance overhead, which I showed you earlier. And we did not include Rega and Para in this analysis because they don't have processor area overheads, the processor chip area overheads. This is because Rega does not change the processor chip, but it introduces intrusive DRAM chip modifications, and Para needs a secure random number generator. So we have more stuff in the paper, more analysis and details, starting with the security analysis that shows Abacus prevents all RowHammer bit flips at all RowHammer thresholds. We also have these analyses, single core performance and energy comparison, and other analysis as well, and some discussion on RowPress. I invite you again to read our paper for these details. And let me conclude my talk. So based on the key observation that many workloads access the same row address in different DRAM banks at around the same time, we developed Abacus, which uses one counter to track the activation count of many rows with the same address across all DRAM banks. And our results show that Abacus induces small performance and DRAM energy overheads at very low RowHammer thresholds, and it outperforms state-of-the-art mitigation techniques. Abacus is also open source and artifact evaluated, and you can check this link and test it. And this will be all for this part of the talk. I'm ready to take your questions. I saw him personally.
Okay. So if a row in one bank has a lot of activation, you refresh that all the siblings row, right?
Yes, all the victims of its sibling rows.
Yeah,
yes.
but when this block bank interleaving, because you are doing refreshing all other banks, and the key idea of bank interleaving is doing that you share access with the other banks. That's yeah, that's the question.
Okay, I'm not sure if I understood correctly, but I will repeat anyway, so you can stop me and ask your question again. So Abacus, let's say that we have one row in one bank that is activated many times. Abacus will still refresh all victims of all its sibling rows. And the key idea of bank level interleaving is I guess I lost you at that point.
Yeah, because when you access, let's say, row 1 in bank 1, you would immediately after that access row 1 in bank 2.
Yes.
But during that time, you're refreshing. You're doing
refreshing
that.
So you're saying that these refreshes, preventive refreshes, could also take some time and bandwidth so that you are not able to access other banks. That's true. This is also the case when you have like preventive refreshes regularly without doing this. But so yeah, we could see some slowdown based on that, but we did not observe a large slowdown coming from that only. I don't know if that explains. Yes, please.
So in slide 26, you described that.
26.
Yeah, 26.
What? Which one?
In slide 36.
36. Okay. Oops. I'm trying to go back.
That's okay.
Okay. Many slides, many animations. So this one.
Yes. So
this is the full slide.
Probably one of the main deals. To use a single counter across multiple banks, is that the number of banks are increasing?
So here, actually, I was explaining why the area overhead of existing mitigations are increasing with the increasing number of banks. So they allocate these counters, or basically calculate these counters, the number of counters, based on basically assuming one bank. And when we multiply it to all like DRAM rows, all DRAM banks, it is like increasing a lot. So what we are trying to do is we are trying to come up with a mitigation technique that scales well when we increase the number of banks. And our observation is that the DRAM rows with the same row IDs, they are usually activated as like similar amounts, right? And therefore, we are grouping them together, basically. And we are using just one counter. Does that explain or answer your question?
Yeah, I was thinking.
Okay.
Second question was, my understanding is that you implement these counters in the processor because you evaluated using cacti.
So we implement these in the memory controller specifically.
So I think everyone is back, so we can start the next part of our lecture. In this part of the lecture, we will be talking about industry solutions to DRAM heat disturbance. Nisa and Giray gave us some presentations about what we have in academia today, and now I will briefly go over what is industry doing to prevent RowHammer. So a brief introduction. I am a researcher at Safari Research Group, and I'm a visiting master student in ETH Zurich. My research interests are in our computer architecture, memory systems, and hardware security. I have a fun fact about that picture. Giray told me to prepare a brief self-introduction slide for this morning, and I realized that I don't have any pictures of myself. And while I was going through my pictures, I realized that I had a picture from a bridge in Buenos Aires from when I presented the same paper that we will talk about today. And I think it's also a nice coincidence that we have such a beautiful bridge while we're talking about industry solutions. I think this is a very principled design example to show that how something can be elegant while satisfying the needs of a design. So this bridge can allow pedestrians to walk through one side to another, and when necessary, it can rotate and allow bridges to pass. And I think in our designs, we should aim for such principled designs. As Giray talked yesterday a bit, in the earlier days, industry solutions, for example, TRR, I think weren't that principled because they decided to go for security by obscurity and believe that, or maybe they thought that their designs would be unbreakable. However, many work show that these earlier versions of the designs were not secure and they could observe bit flips if you reverse engineer them. I'm flashing two papers that bypass these earlier versions of the mechanisms. I think it is getting better today. Industry is no longer trying to be obscure with their design. They are updating their standards and they're openly telling us how these are being, or how these should be mitigated. The latest JEDEC DDR standard as of April 24 introduces a new mechanism that we will talk about today. And by the end of the lecture, I'll let you decide if this is a principled RowHammer solution. So the paper I'm going to talk about today is Understanding the Security Benefits and Overheads of Industry Solutions to DRAM Heat Disturbance. We presented this paper at DRAMSec Research, DRAMSec Workshop, EDISCA this year. Here's an executive summary of the paper. As we mentioned multiple times today, DRAM chips are becoming more vulnerable to heat disturbance. The latest JEDEC DDR5 standard introduces a per evacuation counting mechanism to mitigate these errors. However, no prior work investigates PRAC's security and performance overheads. Our goal in the study is to rigorously analyze and characterize the security and performance overhead of these new mechanisms. Our mathematical analysis and extensive simulations show that PRAC provides security as long as no bit flips occur before accessing a memory location 20 times. PRAC has currently non-negligible performance and energy overheads for today's DRAM chips, and it poorly skews to future DRAM chips that are more vulnerable to RowHammer, where it induces increasing performance and energy overheads. We also show that PRAC is a memory performance attack vector, where an attacker can exploit its preventive actions to mount memory performance attack and hog a significant amount of DRAM throughput. Our implementations and scripts are publicly available in Remulator 2, and I believe most of you use Remulators already. So if you, after the lecture, you have some burning ideas about PRAC, or you want to check the implementation or run some applications yourself, you can just use the implementation or public repository. So I will go through the background fairly quickly because most of this was mentioned today. As you all know, DRAM modules have chips. In chips, we have DRAM banks. In each bank, we have DRAM cells that contain data. These are connected through word lines as rows horizontally, and they're connected to sense amplifiers vertically with bit lines. To access a DRAM row, to access DRAM data in DRAM, we perform three operations. First, we activate a row and bring the data into sense amplifiers. Then we use read and write operations to retrieve or update the data. And then we pre-charge the row and prepare the DRAM bank for access to other rows. Activation and pre-charge operations take time because the sense amplifiers need to read the charge in the DRAM cells and restore them while doing these operations. So DRAM manufacturers set timing parameters to make sure that the data is being accessed correctly. 2 or 3 important DRAM timing parameters that we will talk about today is first TRS, which denotes the minimum amount of time a row must remain active for before we can safely close it, and TRP, which denotes the minimum amount of time you need to wait before closing a row and opening another one. These two DRAM timing parameters combined is denoted as TRC, which is the row cycle time that defines how frequently we can access DRAM rows in the same bank. As you all know, if you repeatedly open and close rows in DRAM, you induce bit flips. In our study, we refer to the RowHammer threshold as the number of activations necessary to induce the first bit flip. You also know that the RowHammer threshold has been decreasing significantly. Therefore, it is important to efficiently and effectively prevent these bit flips. One potential way to prevent these attacks is to preventively refresh victim rows before they observe bit flips. And the industry solutions that we will talk about today are also using this approach. They track or estimate the activation counts of aggressors and preventively refresh victims before they observe bit flips. One might think that, okay, DRAM manufacturers are starting to employ RowHammer mitigations, then isn't it solved? Can't we just track the activations and perform the refresh? A major problem with preventive refresh is when to perform when you're doing the tracking in DRAM module, because the memory controller does not know when a row has been activated many times. And because the preventive refresh is a blocking operation, the DRAM module itself cannot decide to start a preventive refresh, because at any time, the memory controller could try to access those blocked locations and cause faulty operation. To prevent this, one of the earliest JDEC specifications introduced a new RFM command. I think this was around 20 and 20, where they introduced the RFM command. RFM command allows the DRAM module with time to perform preventive refreshes. You can think of this as a contract between the memory controller and DRAM module, where the memory controller is saying that, hey, I won't access this location for a set amount of time. You can perform necessary activations to that location. We will cover two industry solutions that use RFM commands. First is periodic refresh management, or PRFM for short, where the memory controller periodically sends these RFM commands to give time to DRAM module for preventive refreshes. And the second one is the most recent one, per row activation counting and backup, which we will call track, where the DRAM chip internally tracks row activations. And when a row reaches a critical value, it requests RFMs from the memory controller by sending the new backup signal. We will start by looking at the execution of PRFM. Here on the left, we have our memory controller and per bank counters, and on the right, we have our DRAM module. The memory controller determines the frequency to send RFM commands by tracking the activation count of each DRAM bank. In our example, the memory controller sends activations to the DRAM module until one of the banks reach a critical activation threshold, which we call RFM threshold. Once the threshold is reached, the memory controller clears the counter and sends an RFM command to the DRAM module to allow time for preventive refreshes. However, as you may guess, PRFM performs tracking with very low accuracy, because each DRAM bank contains thousands of DRAM rows, and they all share the same counter. Therefore, PRFM results in a high number of preventive refreshes and induces high performance and energy overheads that we will discuss later. The second industry solution, this is the one that has been introduced in April of this year, is PRAC. With PRAC, they decided to couple each DRAM row with a counter that tracks the number of times that it has been activated, so that the mechanism can check these counters or use these counters to accurately refresh the victims of each aggressor row. However, currently, these counters are not perfect because they are not updated in parallel to DRAM accesses, but rather these counters are updated when a DRAM row is closing. Because of this, enabling PRAC increases critical DRAM timing parameters. Yes, I have a table for that. So these are the most important timing parameters that change. As you can see, that some of them relating to the minimum amount of time that we can keep the row open decrease, while the ones that are related to keeping the waiting for another row to activate increases. I think the most important DRAM timing parameters here is TRP and TRC. As you remember, TRP is the amount of time the row must stay closed for, and the TRC is the frequency of which we can access DRAM rows. We will talk about the implications of these timing parameters to performance in a bit. So here I show another memory controller and DRAM module, but this time the memory controller is not performing any tracking, and the DRAM module has per row activation counters. In a PRAC system, the memory controller sense activates until one of the rows reach a critical value, which we will call the backoff threshold. Once the backoff threshold is reached, the DRAM module sends a backoff signal to the memory controller, indicating that it needs time for preventive refreshes. Once the signal is received, the memory controller has a fixed amount of time where it can continue scheduling requests. In our example, the memory controller sends another activates. However, the memory controller can fit 3 more activates into this window. Once the window of normal traffic ends, we enter the recovery period where the memory controller must send n RFM commands. We denote the PRAC implementations based on the number of RFM commands they sent during this period. For example, in our example, the memory controller will send 2 RFMs in the recovery period, and we will call this implementation, for example, a PRAC2 implementation. So these were all described in the documentation that I showed in the beginning of the slides. However, what is not shown here is how you should configure these mechanisms and how secure they are based on their configuration. We perform a worst-case excess pattern analysis. It's been known as the wave attack or the fainting attack in the literature to obtain the maximum amount of activations an attacker can achieve. And we sweep both the defense and attack parameters to obtain the highest activation count possible an attacker can achieve. So I want to talk about the wave attack briefly. So one might think that don't we have these thresholds? Can't we just set them to be less than the RowHammer threshold and they secure against RowHammer bit flips? Let's look at this example in a PRFM system where the RowHammer threshold is 5 and the PRFM threshold is 4. If we attack a single row, we observe that before we can access the amount of activations necessary to induce a bit flip, the controller will send an RFM command and we will refresh the victims of our aggressor, successfully preventing the bit flips. However, we can be a bit more intelligent in our attack and use decoy rows. In the second example, we will distribute our activations across multiple rows. And after 4 activations, the memory controller will send an RFM command and refresh one of our decoy rows. We will continue our attack by attacking the rows that were not refreshed in the previous RFM command, where the memory controller will send another RFM to refresh our second decoy row. At this point, we have a single aggressor that has already been activated 3 times, and we have 4 more activations in the bank. Therefore, we can easily induce bit flips in the system before the next RFM arrives. Therefore, secure configuration of these mechanisms is non-trivial and requires extensive analysis to be secure. So I will share our configurations and security analysis results. On the x-axis, we will see the defense parameters that we set while we are configuring these mechanisms. On the legend for PRFM, we will see the attacker parameter, that is the wave attack size, the number of rows they start the attack with. And on the y-axis, we will see the number of activations possible to a single row. I will show an example on how to read this figure first. Let's assume that we configure our system with an RFM threshold of 256, and our system has a RowHammer threshold of 1000. We consider the bars that are below this line safe, while any bar that exceeds this line is considered unsafe. For a system to be secure against an attacker, all bars for a given configuration must remain below that line. Therefore, this system wouldn't be secure with a RFM threshold of 256. Now I reveal all of the figures to show what each configuration show the security each RFM configuration provides. We observe that PRFM must send RFM commands very frequently to prevent bit flips at relatively low RowHammer thresholds. For example, to mitigate a RowHammer threshold of 128, the PRFM would need to send an RFM command every 8 activations. We repeat the same analysis for PRAC. The x-axis again shows the backoff threshold for the defense parameter. The y-axis shows the maximum activations possible. This time, the legend shows our different PRAC configurations defined in the documentation, and each bar will show the worst case possible attack pattern that we choose for the attacker. So you don't see the wave attack parameters here, but each bar displays the worst one. Once we repeat the analysis, we observe that PRAC is configurable for secure operation against RowHammer thresholds as low as 20, because an attacker can obtain 90 activations to a single row on the PRAC4 configuration. We evaluate the performance and energy of both mechanisms using Remulator 2. We implement both mechanisms in Remulator 2 and extend Remulator 2 with DRAM power to be able to analyze the energy overheads of these mechanisms. We use a realistic 4-core system with a DDR5 module that has 2 ranks and 64 banks total. We compare against 3 state-of-the-art RowHammer mitigation mechanisms. First is graphene, which is the best performing, but as Nisa showed, it has huge overheads as NRH decreases. We have para that consumes the least amount of, among the mechanisms that we discussed, the least area overhead, but has high performance overheads. And Hydra that tries to strike a balance in between by keeping some stuff in DRAM while caching them in the memory controller to be able to keep a low area overhead in the processor chip and low performance overhead as well. We evaluate 64-core workload mixes from different benchmarks. We evaluate 4 types of industry solutions. First is PRFM, as we discussed, where we are sending periodic RFM commands. The second is PREC-N, where the memory controller sends N RFMs with each backup. We combine both and evaluate PREC plus PRFM, where memory controller both sends periodic commands and sends RFMs when a backup is received. And PREC optimistic, which is our hypothetical implementation, that is PREC4 with no change in DRAM timing parameters. So PREC has 2 sources of overhead. The first is that once the PREC sends a backup signal, the memory controller stops its execution and starts sending RFM commands. So that induces overhead. The second is that PREC changes certain DRAM timing parameters and reduces the frequency of which we can access DRAM roles. To be able to assess which overhead is coming from where, we have this hypothetical analysis in our results as well. So I will show our performance results first. On the x-axis, we have the RowHammer threshold, and on the y-axis, we have the normalized performance. We first observe that PREC induces non-negligible performance overheads due to increased access latency, because our hypothetical implementation without these increase in timing parameters does not show such overheads. We also observe that at relatively high RowHammer thresholds, graphene and Hydra outperform PREC. We also see that as RowHammer thresholds decreases, PREC's overheads stay relatively constant, while due to performing preventive refreshes, while once we exceed the RowHammer threshold of 64, we see that PREC's performance decreases significantly. This is due to PREC being vulnerable to a wave attack and needing to be configured for very low trigger configurations. We also see that PREC optimistic outperforms all evaluated mechanisms up until the RowHammer threshold of 64. However, after this point, we see that due to being vulnerable to the wave attack, it does not perform better than these mechanisms. We also see that PRFM system performance overhead significantly increase as NRH decreases. I also show the energy results. In the x-axis, we again see the RowHammer threshold, and the y-axis, we have the energy results. We similarly see that PREC has high DRAM energy overheads due to the increased DRAM timing parameters. And we also see that PREC's energy overheads scale well until RowHammer threshold of 64. However, it has large overheads after RowHammer threshold of 64. And we again see that PRFM's DRAM energy overhead significantly increases as RowHammer thresholds decrease. We also evaluate an access pattern that triggers the most amount of backups with least amount of activations possible. We see that once such an adversarial pattern is used to trigger many backups, we can mathematically plug up to 79% of DRAM's throughput of future DRAM chips, and this results in a degraded system performance up to 98%. We have more results in the paper where we describe each mechanism in detail, and we show more results, or we also explain more about our threat models. We also share simulation results about the memory performance attacks. Our paper is available on arXiv or the RAMSec workshop website, whichever you prefer, and our implementations are fully open source. Now I'll conclude my talk and mention some future directions about PREC. So we rigorously analyze and characterize the system and performance overheads of these newly introduced industry solutions, DRAM meet disturbance. Our evaluations show that PREC is secure against RowHammer thresholds down to 20, has high performance and energy overheads for today's DRAM chips, and it poorly scales to future DRAM chips, inducing higher system performance and energy overheads. We also show that PREC can be exploited as a memory performance attack vector, so with a significant amount of DRAM's throughput. We conclude that more research is needed to improve PREC by first reducing the overheads due to increased DRAM timing parameters at high RowHammer thresholds, solving the exacerbated performance impact due to wave attack as RowHammer thresholds decreases, and stopping its preventive refreshes from being exploited as memory performance attack vectors across all RowHammer thresholds, basically. Thank you for listening. that concludes my talk. I can have any questions if you want, if you have any.
So which of the four mitigations are used in the industry, like on DRAM chips?
Okay, so you're talking about the configurations that we evaluate. These, right?
Yeah, which of the four are used at the moment?
So track is new, and we hypothesize that. So if someone could have implemented and we wouldn't know. For example, Professor Mutlu showed some slices where there were like patterns showing that they have RowHammer counting cells, right? As far as we know, track is not out there yet. So DRAM chips don't have track implemented. However, I think RFM has been out for a while, and if someone is implementing, it's probably on RFM. So the first one is probably out there, and the other three is not at the moment.
It's just the JDAC says it's possible, but it's not.
It's optional at the moment. Track is it's also very new, so it's like came out in April, so it's very hard for them to roll out chips and memory controllers that support this, because changing the DRAM modules is not enough for this. You're providing the DRAM chip with to become an intelligent agent, not fully intelligent, but a partially intelligent agent, and the memory controller needs to obey that. So the processor also needs to support it. So we will need better memory controllers. I'm not sure if it's possible with a firmware update, but you need both.
Would the DRAM chip issue the track signal, like during a read request, or?
It sends it when a row is closing. So once you close a row, it reads the counters and increments them. At that time, it can understand that it's hit the threshold and send the signal. And it's not an instant signal. It has some latency because it's on a slow path. But it starts asserting the signal while the row is closing.
Would it be the case that memory controller is issuing some other command at the very moment, or is it not possible?
It can be. That's why we have the window of normal traffic. So you have a duration for the memory controllers to. So you're not cutting the execution in place. You're just indicating to the memory controller that it should start sending some RFM commands in the near future. So you can have some slack. It's not that instant.
Do you have some attack patterns in your mind to work around this?
No, not at all.
It sounds like that from the question.
Can you go to the wave attack schematic?
Yes. Sure, festival.
Yeah. So I did not get why could increase beyond 4.
So this is a hypothetical system where you're saying that why it can't go above 4 without being refreshed, right?
Yeah.
So this is it is because we are evaluating like a PRFM system. So we configured the RFM threshold to be 4. So for every 4 activations to a DRAM bank, the memory controller sends an RFM command. So that's the period. 4 activates, 1 RFM. 4 activates, 1 RFM.
So the mirror row could go beyond 4.
Yes, in the second example we do. It induces bit flips because we use the wave attack. So maybe I'm not understanding the question.
So the memory controller did not send the RFM command for this row.
So the RFM command, so there are parts, so there are different RFM command versions. The one we're talking about just gives you a bank group or bank address and tells the memory, tells the DRAM module that you can do your operations for that bank. The tracking is done by the DRAM module. Therefore, it's not saying that refresh that row, refresh that row. It's just saying that perform refresh operations in this bank. And the DRAM module is responsible for refreshing the maximal activated row. So we are basically overwhelming so because the period is set, period is constant, we are overwhelming the mechanism here.
Okay, so it was not in the plan that I will deliver this lecture, but Hasan had a health issue, so he needed to go see a doctor. So I'm covering for him. I hope I will deliver it in the best way possible, but yeah, help me out here. Ask questions during the talk as well, so we can have a more lively discussion. So this talk is about RowPress. So yesterday I mentioned RowPress a little bit. I talked about the memory access patterns, how you can play with the memory access patterns, and you can make the read disturbance exacerbated. And here is the full paper that actually explores that. So within this talk, I'm going to talk about this paper And there's a follow-up that was published this year in the SN conference in 2024. I will talk about that as well, and also some other works from other groups that explore this phenomenon. So the high-level summary is we demonstrate in this paper and analyze a new read disturbance phenomenon that we call RowPress that causes bit flips in real DRAM chips. And we show that RowPress is a read disturbance phenomenon that is different than RowHammer. And hopefully I will convince you that it is different by showing some experimental data. And we demonstrate that RowPress can be exploited in a user from within a user level program. We just have a proof of concept for that, but we are expecting security researchers to come up with more effective attacks. And we also provide some effective solutions to RowPress in this paper. So what's RowPress? If you hammer some rows, but while you're hammering, if you keep your row open for longer time, then it has an additional read disturbance effect. Basically, it's purely based on keeping a row open for a long time. And when you do that, you can cause bit flips in adjacent rows. And these bit flips do not require many row activations. And in extreme cases, only one activation is enough to induce a bit flip. So let's see the experimental data. Okay, here's a more pictorial description of this memory access pattern. I already presented to you yesterday, so I'm not going to go over it. But essentially, as you increase the time your row stays open, you can reduce the necessary activation count to induce a bit flip. Okay, so RowPress significantly amplifies DRAM's vulnerability to read disturbance, and it has a different underlying failure mechanism from RowHammer. These are our two key takeaways from the experimental characterization. Let's talk about the characterization work a little bit. So we use this FPGA-based infrastructure. Again, it's the same infrastructure called DRAM Bender. And we have the same temperature control, and we have fine-grained control over DRAM commands, timings, etc. In this work, we test 164 DDR4 DRAM chips from all three major manufacturers. And here, the names are already disclosed. And as you can see, it covers like multiple manufacturers and different die densities and revisions. So whatever we explore in the following results is something common across all these modules, unless otherwise specified. So the major takeaways, I already talked about them. So the key characteristics of RowPress are like it amplifies the read disturbance in DRAM in the sense that it reduces the minimum number of row activations needed to induce a bit flip, and this reduction is as large as like 1 or 2 orders of magnitude. And in extreme cases, only one activation is enough, and it gets worse as temperature increases. It is different from RowHammer because it affects different set of cells. When you look at the intersection of the sets of cells that are vulnerable to RowPress and RowHammer, it seems quite disjoint. And it behaves differently as access pattern or temperature change compared to RowHammer. Okay, so let's look into the first set of experiments that result in the first key takeaway. So now we check how minimum activation count induced the first bit flip changes as we keep rows open for a longer time. So in this plot, this is pretty much the same organization for across like a lot of plots in this paper actually. So on the x-axis we have the aggressor row on time. So it specifies when we open a row how much, for how long we keep the row open before we send the pre-charge command. So from left to right, it increases from 36 nanoseconds to 30 milliseconds. And we marked some important points. 7.8 microsecond and 70.2 microseconds are important points because you need to send a refresh. So there are two types of refresh. Two types of refresh scheduling that's performed today for DDR4 DRAM chips. So you either send a refresh command every 7.8 microsecond. So when a refresh comes, you need to have your rows closed. So you need to send a pre-charge. So you cannot keep your row longer than that time. And there's an extended refresh scheme where you can actually have 70.2 microsecond of time window between two refresh operations. So you can keep your row open for that much time. And here the shade around the curve shows the minimum and maximum. I forgot to tell you that the y-axis shows the minimum activation count needed to induce the first bit flip. So the leftmost point, where we keep rows open for 36 nanoseconds, is the RowHammer access pattern. And as we go from left to right, we actually have first a mixture of RowPress and RowHammer, and it goes to RowPress later on. And you can see actually in the first part, there's some plateau until this point. And then you see that the minimum activation count needed decreases a lot. So that's where RowPress becomes more dominant. Okay, I already talked about this. And yeah, please pay attention to the slope. On the y-axis, it's a logarithmic scale, right? So between every ticks, actually, we go from like, we go down by an order of magnitude. Okay. So here is the curve. So this curve was only for one module, one die revision, manufacturer Samsung, 8 gigabit C die. And this is all die revisions from manufacturer Samsung. So each curve corresponds to a different die revision and density here. And the common thing is, so the important thing is the behavior is common, right? We see same decrease in all of them. And this is data from all three manufacturers, so we see some similar patterns. And based on our, among the chips that we test, ACM reduces by 21x on average when Tiagon increases from 36 nanoseconds to 7.8 microseconds. So it's quite practical to do, actually. And in the extended region, you can even go for 191 times of decrease. So RowPress significantly reduces AC min as Tiagon increases. Okay. So here we look at what are we looking at here? Okay, so here we look at the effect of temperature here. So here the data, any data point below 1 means fewer activations to cause bit flips. So here on the y-axis, again, we have the AC min, but now it's normalized. So we run our test at 80 degrees Celsius, and then we normalize the value to the value at 50 degrees Celsius. So it shows you how much it's affected by increase in the temperature. So if the data point is below 1, then it means that fewer activation cause bit flips at 80 degrees compared to 50 degrees. And as you can see, in the beginning, when your Tiagon is low, then there's not much change actually with the temperature, right? This is like average across a lot of cells anyway. And as you increase Tiagon, there's a significant decrease around this region, around this region, around this region, and all these are like below 1, right? So it shows a very strong correlation with maybe I shouldn't say that, but relation, let's say, with the between the temperature and the RowPress vulnerability. So when you increase your temperature, RowPress gets worse. Okay, so this is our takeaway. This is actually part of the proof of like the difference between RowHammer and RowPress actually, because in RowHammer, if you remember from yesterday, it has a bit more complex relation with temperature. When you increase temperature, it doesn't necessarily mean that RowHammer will get worse all the time. But for RowPress, it's a more straightforward relation with temperature. Okay, let's look at the difference between RowPress and RowHammer. So we look at the cells vulnerable to RowPress and RowHammer in this plot. So basically, we just calculate the population of the intersection between RowPress vulnerable cells and RowHammer vulnerable cells. So this overlap is like the fraction of the intersection over union, right? And here you can see that we have a large population when the aggressor row on time is low here, and as you increase it, it suddenly goes to values very close to 0. So it means that as RowPress gets more dominant read disturbance effect going from left to right, the intersection of RowPress and RowHammer vulnerable cells actually decrease a lot. And 36 nanoseconds, for example, is actually pretty much RowHammer anyway. So on average, only like this small fraction of DRAM cells are vulnerable to both RowPress and RowHammer. So it tells us that these are actually inducible bit Phillips in different types of cells. And most cells are vulnerable to RowPress. Most of the RowPress vulnerable cells are not vulnerable to RowHammer. Then we look at the directionality of the RowHammer and RowPress bit Phillips. So directionality means that do you flip bit from 1 to 0 or 0 to 1? And the observation based on these tests is that the majority of RowHammer bit Phillips flip from 0 to 1, but RowPress bit Phillips are more dominant going in direction 1 to 0. So there's another difference in this behavior. And the last piece is the effectiveness of the memory access pattern in terms of your hammering or pressing from one side or from two sides. So the takeaway is that as T-agon increases, single-sided RowPress becomes more effective compared to double-sided. So here on the y-axis, it's a bit complicated, but let me walk you through that. So we have the difference between single and double-sided AC min. So data point below 0 here. So we compare these two AC min values in cases of double-sided and single-sided access patterns, and we get the diff of that, right? So if the diff is below 0, then it means that fewer activations are necessary to cause bit Phillips in single-sided RowPress compared to double-sided RowPress. And as you go from left to right, again, you make RowPress a more dominant read disturbance phenomenon, then the single-sided attack or access pattern becomes more effective than the double-sided one. And this is completely opposite of RowHammer. Actually, you can see RowHammer point here as well on the left side. In RowHammer, it's a very widely accepted observation that double-sided attacks are way more effective than single-sided attacks. Okay, we already talked about sensitivity to temperature, actually. So I'm just going to skip that. And I'll talk about some real system demonstration. As I said earlier, this is a proof of concept in this paper. We use a i5-based system that uses a Samsung module that we verify that it implements a TRR mechanism to mitigate RowHammer bit Phillips. And yeah, our key idea is to proof of concept RowPress program that keeps a DRAM row open for longer by keeping on accessing different cache blocks inside the same row. So this is our example code. Basically, you go access an aggressor row, and then you go access like another column in the aggressor row, another column in the aggressor row, and after that you flush all the data and then go back to the loop. So here, as increasing the number of cache blocks that we access, we try to keep the row open longer. We actually put some incentive to the memory controller to keep the row open longer. And we have a test on 1500 victim rows that shows that as we increase the number of cache block reads, we can actually start seeing some bit Phillips that we would not see before. So on the x-axis, you see the number of cache blocks that we read, and on the y-axis, it's the total number of bit Phillips. And as you go from left to right, first you don't have any bit Phillips, and then after some point you start seeing bit Phillips. And basically, leveraging RowPress, our system induces bit Phillips that you cannot Phillip with using RowHammer. So this paper was published in ISCA 2023, as I said earlier, but later on we kept working on this paper. So if you look at the full paper, actually on the archive version, the original paper is supposed to be like 11 page long, and you can see almost like 10 pages of appendix or something like that after that. So the paper size actually almost doubled. That's because like we tried, we went more rigorous even after the paper published. So it's a general tendency that we do in our group actually. The research doesn't stop when you publish the paper, so we keep improving it. So in this example, this algorithm one old is from the paper that was published as the ISCA version. And then later on, we improved this real system demonstration by using algorithm 2. We did just like this small change here. This flash operation goes to top so that you access the memory more frequently. And as a result of that, you can induce even more bit flips. So I guess it's important to see that you can induce bit flips, but it's also important to say that when you play with your code a little bit more, you can improve it. So there is actually some headroom for improvement. So RowPress is a new read disturbance phenomenon. Think about RowHammer. It was first discovered, let's say not published, but discovered in like 2012, because the work started around that time. And then it was published and widely known by 2014. And we had all these like sophisticated attacks over the last decade, right? This is just discovered like last year. And this is just some proof of concept demonstration on real system. So, and this actually changed a lot of things because it reduces the necessary activation count in induced bit flip quite a bit. Now, if your RowHammer mitigation mechanism is configured for like a activation count of, let's say 500, and by using this, you can induce bit flips at like 300 activations. Now you can just bypass them, right? So there is a lot of opportunity from system level research perspective as well. So how can we mitigate RowPress? So we propose a methodology of adapting the existing RowHammer mitigation mechanisms so that they can also mitigate RowPress. And how we do that? We basically take the raw open time into account. And here on the x-axis, you see like the raw open time. When you go left, it means less raw buffer locality. When you go right, more RowPress, more raw buffer locality, more RowPress, and you have more disturbance. On the y-axis, we see the minimum activation count to induce the first bit flip. So this is a cartoonish picture of how it changes based on the experimental data, right? So instead of configuring your RowHammer mitigation mechanism at this orange point, what you can do is you can limit the rows open time by changing the row policy in your memory controller. You can ensure that even if you have upcoming accesses, you can close row at this point. So based on this curve, you can get your RowHammer threshold from this y point to this point. So by doing that, you can actually protect against RowPress. By reducing the threshold, so so we explain this like this in the paper. You can also think of like from the other way around. Instead of reducing the threshold, effectively you can do the same thing by if you observe that a row is staying active for longer time as you go, like in the memory access pattern, you can just keep incrementing the activation counts as well, right? So if you don't close row for like, let's say 50 nanoseconds, you can increase activation count by 1, even if there's no new activation. So when you do that, the activation count will increase more rapidly, and it will reach the original threshold. So it's effectively doing the same thing from the other way around. So there's another paper actually in the field that will be published in Micro this year, like next month, basically, called Impress that does that. So these are our evaluation results for. So we adapt 2 of the existing RowHammer mitigation mechanisms, graphene and para, by doing this change. And here are our performance overhead results. And we conclude that our solutions mitigate RowPress at low additional performance overhead. Okay, so the conclusion is that we demonstrate this RowPress, a new widespread disturbance phenomenon. We characterize a lot of chips, and we demonstrate that we can exploit RowPress from a user-level program, and we provide effective solutions to RowPress as well. So the good thing is all the methodology, everything is open, everything is available on GitHub, and their artifact evaluated as well. So I guess there is this website called Zenodo. I guess they are there as well. So you can find all the necessary information there. Okay, so the interesting question. Now we have RowHammer, we have RowPress. What if we combine them? So if we craft an access pattern that is partial RowHammer, partial RowPress, can we make the attack even more effective? So we are looking for this kind of question. Do you think it's reasonable? Or maybe before this, I should stop and ask, like, do you have any questions about RowPress? No? Okay. Any ideas about combining them? So we did some initial experiments. So basically, we have these two rows as our aggressor rows, and we keep hammering one of the rows while pressing the other one. So they're attacking to the same victim row over there, right? And this is a paper that was published in the Disrupt track of DSN conference in this year. We basically combine these two access patterns, and we test these access patterns in 84 different DRAM chips from 3 major manufacturers. And our key results show that combined pattern takes significantly less time to induce the first bit flip compared to both RowPress only or RowHammer only. And the initial bits that flip are different across RowHammer, RowPress, and combined patterns. And our hypothesis is that the read disturbance caused by RowPress from one of the two aggressive rows in a double-sided pattern is much more significant than the other one. So our baseline access pattern is like single-sided RowHammer or RowPress here, and basically we use the TIAGON parameter again and sweep it from 36 nanoseconds to some other values. And this is our conventional double-sided RowHammer RowPress attack. So we have the row 3 as the victim, and we sandwich it from both sides here, right? And we again sweep the TIAGON value for them. So when we combine them, we have two different TIAGON values. So we can perform RowHammer for one, RowPress for the other one. And we use the same infrastructure again, and we look at the two metrics. One of them is the time to first bit flip. So please go ahead.
How do you perform a double-sided RowPress attack? Because when you want to do a RowPress, you keep having the same row in the row buffer, right? Because you need to keep it open. So how can you have both rows pressed the same?
It's not simultaneous. So you open one row. Okay, the question is like, how can you perform double-sided RowPress if you can only activate one row at a time? So you open one row, you press it for some time, you close that row, you open the other row, and then you press it sometime as well, and then close, and then do it repeatedly.
I know, I was wondering if you can like find the row between like one in one subarray, one in another one, and press a different subarray because subarrays are different row buffers, or it doesn't make sense.
It totally makes sense. Not with maybe with current chips as well. I'm not sure. So the thing is, based on the DRAM communication protocols, you can only open one row at a time in a DRAM bank. Even though you have subarray level parallelism and you have the row buffer separate for each subarray, unfortunately you cannot open like two rows in different subarrays at the same time. This is by the JEDEC specifications. You know, if you operate the DRAM chip in the recommended conditions. But I'm guessing that, yeah, actually, Onur already talked about it last week, and Ismail will probably talk about it sometime soon, that in real DRAM chips, you can actually do that. You can open more than one row, actually many rows all of them at the same time. And think about the effect of RowPress if you just open like 32 different rows all together. Another project, just say. The question was like, how can you open can you open 2 different rows in 2 different subarrays so that you can simultaneously press different rows? Okay. And we look at the AC-min. You're already familiar with AC-min. So these are the chips that we test. I'm not going to get into details. And let's look at this results. So the green curve shows the single-sided RowPress or RowHammer, and the orange one shows a double-sided attack, and the purple, or I'm not sure which color is that, purple, blue, something like that, shows the combined. I'm referring to this curve. And the important thing that you need to see here is that the blue or purple curve is below the other curves, right? So on the y-axis, we look at the time to first bit flip. So it means that for a given aggressor row on time, if I put a line over here, for example, then it cuts the blue sooner than orange and green. So basically, by playing with your access patterns, by getting a hybrid of RowHammer and RowPress, you can actually reduce the time that you need to induce the first bit flip. This is the total time of the attack. And these are some significant reductions. And you want these in real life attack scenarios because it means that the malware detection system, for example, does not have enough time to detect your attack. Okay. So here we look at the same comparison, but this time for the total activation count, and we see that by combining patterns, you can reduce the necessary activation count quite significantly. So while you're pressing one row and hammering the other row, you can actually reduce the activation count to the level that you're pressing the row, right? But then since you're hammering the other row, the total attack time gets much shorter as well. Okay. And this is common across all 3 manufacturers. So I guess I already talked about these, and the hypothesis is that when we do RowPress from one side, like one of the aggressor rows, have more effect on the victim row compared to the other one. And there are more results in the paper, bit flip direction and the overlap of bit flips, similar to the RowPress paper. And you can see all of them in this full paper. You can access from the QR code, and you have all the slides already uploaded on the course web page, so you can find them. Okay, for the interest of time, I'm gonna skip the conclusion. I already talked about all those, and I'll move to more low-level discussions. If you don't have any questions, but I can get questions, yes.
Has there been comparison of the total attack time with RowPress and the total attack time with just Row? Because, I mean, as far as I can recall, we've only discussed AC-min, the number of activations, but with RowPress, because you keep it open so long, the calculation would be different. The amount of time you keep it.
Yeah, exactly. Is it this one? No, not this one.
Okay.
So this is not showing it completely, but yeah, I think you cannot see it here. So the question is like, do we have a comparison of the total attack time for RowHammer and RowPress? That data should be inside that ISCA 23 paper. Check the extended archive version. It should be there, I think. I don't have it in these slides.
Also, does it decrease with RowPress?
It's not on top of my head.
Okay.
Yeah.
Because, I mean, changing the number of activations is okay, but at the end, we want, if the time decreases, it's a more bigger problem.
So it depends. The question is like, does the time, the total attack time decrease is the bigger problem? So it can be a bigger problem if you're racing against those like system level malware detection systems, antivirus software, blah blah blah. But at the same time, let's say your RowPress takes longer than your RowHammer attack, but you have some very robust RowHammer defense mechanism configured for a high threshold. And with RowPress, you can achieve bit flips with low threshold, right? Then the attack can take longer, but you achieve bit flips, while with RowHammer, you cannot get bit flips. So I think the approach should be like considering all of those altogether. Other questions? Yes.
So if I recall correctly, you mentioned that RowPress and RowHammer have different ideal temperature at which they tend to work better. I think you said that RowHammer is often a very specific zone temperature, whereas RowPress generates something different and works better the higher the temperature gets.
Yes.
So what I'm talking about is kind of combined attack, because you gave data which showed that it's more effective. I don't think you mentioned the temperature to which the data is collected. Is it perhaps the case that, well, if you find a specific temperature, combined attack is better versus a high temperature, maybe pure RowPress? Or is there a heuristic to determine within a given temperature band which of the three is better, considering now your added possibility of doing a combined attack?
That's a very good question. Yes. So I need to repeat the question. So essentially, does a combined RowHammer RowPress attack work better at all temperatures, or because like RowHammer and RowPress have different sensitivities to temperature? Do we take into account? I think in this work, there is not an extensive temperature study for this combined attack. So the thing that you said about like maybe there's a temperature point that RowHammer only or RowPress only works better than a combined. It's possible, yes. Or you can, about RowHammer's temperature sensitivity, it also varies across DRAM cells a lot. And you can find DRAM cells that are like highly vulnerable to RowHammer at, let's say, 80 degrees Celsius. And you know that RowPress gets worse as temperature increases. So you just crank up your system's temperature to 80 degrees, and you will get a better combine. So anything is possible, I guess, in that front. Okay. Other questions? Go ahead.
There was a slide that we saw which showed like 70.2 microsecond to 30 milliseconds. How RowPress counts decreases.
Yeah.
There you go.
Let me see if I understand. Are you talking about this plot?
So the line from 70.2 microsecond to 30 milliseconds, is that extrapolated or is it actually observed?
So this is based on the FPGA-based experiments, right? So we can easily go to 30 milliseconds. It's very easy test to do on an FPGA-based platform. So this is real data from real chips. It's not extrapolation.
So FPGA based, but it's actually a real DRAM.
Real DRAM chip, yes. So you plug a real DRAM chip to an FPGA board, and in FPGA board we don't have a memory controller. We have our own designed DRAM vendor, and it allows us to do this test. So if you just try running that test on your laptop, for example, it's not possible. You cannot keep that open for 30 seconds.
Yeah, it looks too linear.
Yeah, it doesn't look very linear actually when you zoom in, but it looks linear because both x and y axes are like in log scale here. Okay. Do you have other questions? Okay. So here's a list of papers, not to scare you, just to give you more data points or pointers that you can check. But this is about like this is a not very comprehensive, but I guess we have pretty much all the essential papers here that talk about the circuit level mechanisms that cause these read disturbance issues. So how many people are from DTET here? How many people are from DTET? A lot. Okay. So if you guys are curious about the circuit level phenomena, I guess you can appreciate this more. For deaf people, it's usually not that interesting, but I think it's really important, even if it can be boring or painful sometimes. It's really important to understand these things actually. So I'm gonna go through some brief overview of this, and then I think we will conclude on time. So this is how your DRAM array looks like. So far we were putting some like circles in a two-dimensional array, and they were connected to word lines and bit lines, right? So here we have our these like vertical light gray bars are our bit lines, and the horizontal dark gray ones are the word lines. So you basically put a high voltage on this word line, and then you activate some cells, right? So in this today, this is more like the 6F square is the it's like considered as like the state of the art or the common layout in like today's modern DRAM chips. So here the goal is okay. We need to keep in mind that the goal is here to increase density as much as possible, right? So here we do not put like DRAM cells, like one DRAM cell here, another DRAM cell here, another DRAM cell here. So DRAM cells are actually in this tilted way. So we have this thing called active region, this blue part here. And on the blue part, on both sides, we have two storage nodes. So these storage nodes are essentially your capacitors. And so this is like a top-down view, right? So we look at the chip from top, and we see like two capacitors here, and there is a bit line contact, which is drawn as red color here, that overlaps with the bit line. So basically, this is the contact that connects your DRAM cell to the bit line, and this blue part, the so-called active region here, forms a transistor. And your capacitor is connected to this orange part. So basically you have this one capacitor, one transistor DRAM cell implemented in this way. So now we will look at this cross-section in this axis. So this was like top-down. We will look from like this side. We will look from this side now. It looks like this. So the color coding is the same. So you have the storage node contact, the orange or yellow ones. I'm not really good at colors. And this is your bit line contact, and you have the bit line over there. So basically, this is your bit line connection, and this is your DRAM cell, and this forms an access transistor here. And this, excuse me, this AWL is called the it's the word line over there. Okay, so once you put high voltage to your word line, essentially it forms so it attracts some electrons around the word line from the substrate to here, right? Some electrons are accumulated here by high voltage here, and as a result, you have a channel between your storage node and the bit line. So that makes your access transistor. And since these two word lines are too close to each other, and they are sharing the same substrate here, the same active region, there is a capacitive crosstalk between them. This is like one mechanism that causes these DRAM disturbance issues. So essentially, when you put the like high voltage on the victim capacitor and low voltage on the aggressor capacitor, and you activate this word line. As a result, you have some electrons passing and then forming a channel over there, right? And since this is low voltage here, this is high voltage here, there are some electrons moving in this direction. And once you close the row, these electrons are released. So they were in the part of the channel here. And now you do not attract them by putting high voltage in this aggressor row. So as a result, these electrons are just like going wherever they want to go, right? Based on like wherever they're attracted to. And some of them just go back to the like base here, the substrate, the remaining parts. And some of them actually go to the other word line because, sorry, not other word line, the other storage node somewhere here, because this is like the same region. So you don't have isolation between these two cells' active regions. So this is like important cause of the DRAM disturbance. So this movement of electrons also creates some charge traps here. Sorry, there are already some charge traps here, and they can capture electrons. And when electron gets stuck here, for example, for this charge trap, you can see that it's, I mean, it doesn't have to show it in this picture actually, but there can be some charge traps in the oxide of this word line as well, or the gate of the access transistor. So when you have some electrons stuck there, they exacerbate charge leakage. And that's another reason that you have read disturbance here. Okay. So I'm not sure what I was explaining here. So okay. Okay. So in this case, passing word line is on. So yeah, I didn't talk about this. So in one active region, we have two word lines going through the active region. And outside of the active region, we have also two other word lines that are, so the active region stops here. It doesn't go to this side, right? But there's a word line. So we call these passing word line. So these are not connected to these two cells, but they're connected to some neighboring cells. Maybe I can refer back to here so that it's easier to understand. So for this cell, these two word lines are going through the active region, but these two word lines are going to go, those are the passive word lines. So this is like the other adjacent of this row, right? And they are not used for this cell, but they are used for this cell and this cell. But they are so close to each other because we have this tilted layout here, and it's all for improving density. Okay, so once you if you activate this passive word line, what happens? So you have high voltage here, and then you have some electrons accumulated here, right? They're attracted to the high voltage. And then once you release this, these electrons can go anywhere. So these consider that these electrons are coming from like anywhere in the active region. And then when you release them, some of them can go to the storage node, and some of them can get stuck around there as well. And that causes the exacerbated leakage. So yeah, not all electrons return. So when you have double-sided RowHammer access pattern, you basically hammer one active word line, one passive word line all the time, because like those are the two neighbors of, let's say this DRAM cell is your victim. You hammer this word line and this word line. One of them is active, one of them is passive, right? So so when this one is off and you turn on PWL, it accelerates the electron migration from this active region to the passive word line, this edge basically. And when you yeah, basically it traps more electrons here, and it's basically how we explain like RowPress here actually, but this is not the slide for that. Okay, I'm missing one slide here, I guess. Maybe we can repeat this class with Hasan later on. But essentially, when you have these two aggressor rows, one of them is AWL, the other one is PWL. One aggressor row is on, the other one is off. And once you activate this one, you attract electron this side. Once you activate this, you attract electrons this side, and they get stuck around the victim row, and this causes the RowHammer. When you do this very frequently, the electrons go back and forth very frequently, and there is a higher chance that they can get stuck and they can exacerbate charge leakage. So it's why double-sided RowHammer is better than single-sided RowHammer. But when we look at the passing gate effect only, this basically performing a RowPress kind of access pattern on this passive word line attracts all the electrons here, right? And then as a result, you have more charge leakage here. And it also indicates that, you know, the single-sided might be better in the circuit level. And that's what we see in our empirical observations on real DRAM chips as well. Of course, this kind of studies require like more understanding. So there are several groups. I will show you the list of papers again. I encourage you to take a look at them. There are several groups that does physics simulations actually by modeling all this circuitry, and they observe like which electron is going where essentially, and they measure all the like exacerbated charge leakage as a result of that, and try to understand. We have some limited understanding today. We need more. And there are more aspects that we need to cover. But so far, I guess this is all I want to say about this. So, are there any questions? Yes.
So, looking at the pictures you showed us of the constructs, could you maybe make sure that if you do one side equal on our it would be that there are two vector rows, but one of them should maybe affect more than the other, because it's like asymmetric, which one is in your active region and which one is the passive.
Yeah.
So is there any asymmetry that you've observed with one-sided attacks?
Yes. Actually, there were some modules. So the question is there an asymmetry in double-sided attacks aggressor rows?
No,
The effect.
One-sided. So
One-sided.
yes. So like.
Yeah. Okay. Okay, I understand now.
Okay.
So we perform single-sided access pattern, and depending on if we choose a passive word line or the active word line, is there any effect? In some modules, actually, there's a significant difference. So you hammer this row. It was particularly in some micro modules. You hammer this row, and then you observe bit flips in this row. You hammer this row, you observe bit flips in this row. But whatever other row you hammer, you don't observe bit flips in these two rows. So hammering this one does not induce bit flips in this one, for example. So it was something really particular in micron chips. Some of them. But at the same time, we also observe this. So you hammer this, and then there are a lot of these cells next to each other, right? So you get a bit error rate across the whole row just by hammering this on this victim row. So put that on one side, and then you hammer this and this one in a double-sided manner. Then you observe more bit flips in this row. So double-sided still makes an addition, but single-sided on the passive word line was not really effective to induce bit flips. Again, this is only true for like a small subset of the chips that we tested. For many, for the rest, it's like from both sides you can just do single-sided and induce bit flips. Other questions? No? Sure.
So sometimes we affect the rows that are not direct next to us when we hammer. So is there any mechanism that explain it? Like that we, for example, somehow attack a row that's two rows?
Yeah, so consider that you're basically you're attacking this passive word line. This is your immediate adjacent. This is your like adjacent in, not adjacent, neighbor in like 2-row distance, right? So you can also attract some electrons from here, and they can also travel to there with a low probability, way lower probability. So you need many more attacks here. So this is what actually the half-double paper showed. They do a lot of activations to this passive word line, and then some additional activations to this one. And also the victim refreshes activate this as well, assuming that they will refresh this row. And then as a result, the cumulative effect induces some bit flips in this row.
Then with this, like for this code, it's impossible to RowHammer distance tree, right? So you can only hammer your neighbor and to your neighbor's neighbor, but you cannot hammer more than that, right? If you hammer PWF, you can reduce some bit flips in PWF, like the left one, the right one, but after that you cannot go, right?
Yeah, so maybe I should go to this one. So you hammer this word line. You can induce bit flips here, like across this active region, let's say. And the active regions that this word line is connected to are like quite far from this word line. So there's always a gap in between in this like cartoonish picture. So you would expect like the effect being much lower, right? That's another thing that people keep investigating actually. So I don't have a definitive answer, so I cannot say that it's impossible to do that. There are some papers that claim that when you hammer a row, you can observe bit flips in 6 different rows. So where those 6 different rows are located, it's not very clear, but yeah. So there are those kind of observations. I saw a hand over there somewhere, but no. Okay. So I was supposed to talk about the simulation infrastructure and the testing infrastructure as well, but we don't have time for those. It's already 4 p.m. now. So I guess.
We will cover them later.
Do you have any announcements before we finish?
Yes, homework one is gonna be released.
Okay, you will have homework 1 release tonight or the following day or? Tonight, okay. It will be tonight. And you will have 2 weeks, right?
Yes.
And there are some paper reviews. There are a lot of, not a lot of, some exercises. Don't get scared. As you do more paper reviews, you get more bonus points. So keep that in mind. And please submit your homework before the deadline so that you get the full grade, hopefully. Other? Yeah.
For paper reviews, we have time until the end of January. But exercises should be done before the deadline, and we have it like part of the time. So you're not able. So after the deadline, don't email Lisa or write that, oh, I missed the deadline, I need to resubmit.
Yeah, also please consider that, you know, in the last minute, there can be always some issue with server, you know. Okay, yeah, thank you very much.